Hi everyone. Today I will explain you how to handle two formulations within the same dataset and how to develop a model for this situation. I will consider two different situations. The first one is a parallel design where patients have received either formulation A or formulation B, and I will then explain you how to handle the crossover design where A and B have been given in a random order to all individuals. The first thing we need to note when we have two different formulations of the same drug is that once the drug is in the systemic circulation, the two formulations are indistinguishable. So we expect the distribution and the elimination to be the same for both formulations. On the opposite, the absorption can differ, so both the absorption itself and also the bioavailability. To model such situations, two options are possible. I can either have the case where I want to use the same model, meaning the same equations for both formulations, but with different absorption parameter values. So that would be, in this example, same volume, same clearance, but formulation A would have KAA and T lag A, while formulation B has KAB and T lag B. In some cases, I will need two different absorption models for the two different formulations, so that would mean different equations. In this example, I could, for example, have a zero-order absorption process for formulation A and a first-order process with T-lag from formulation B. Let's first see how to handle the first situation. I have loaded a dataset corresponding to a parallel design where I have a column for the identifier, time, the observations, the amount, and a formulation column which has either A or B depending on which formulation has been given. And I will tag this formulation column as a categorical covariate and accept the dataset. Let's have a look at the dataset in the data viewer. In the data viewer, the formulation categorical covariate appears here. I can allocate it and then use it to color or split the data. If I color by formulation and if I zoom on the absorption phase, I can see that the formulation in black, so formulation B, seems to have a larger T lag and then a larger absorption rate. If I unzoom and check what happens in the elimination, it seems that they have the same elimination rate, which is expected. I see only a straight line, so I will try a one compartment model. So I'm closing that Explorer, going back to Monolix and clicking Next, and I will use a model from the library. As I said, we have seen that we have an oral administration. I will need a lag time. I will try a first order model with one compartment and a linear elimination and use the parameterization with the elimination rate. For the initial estimates, I can click the auto init button, select those values as my initial parameter values. I arrive on the next tab, and here what I will do is to add the formulation categorical covariate on T-lag and Ka, such that two different typical values for T-lag and Ka will be estimated. If I look at the formulas, by default, A is considered as a reference formulation, and this is because A comes first in alphabetical order. If I would like B to be the reference one, I could add a new discrete covariate, allocate the A and B groups, and set B as the reference. In my case, I'm fine with A being the reference. So once the model is set up, I can select which task I want to run, save this as a new project, and run it. If I check the Results tab, I can see the estimated value. So T-lag pop and Ka pop are the typical values for the formulation A, which is my reference category. For the formulation B, I will have to calculate a typical value using the betas according to the formulas here. Let's do that on the slides. So the typical value of Ka for the formulation B is Ka pop times exponential of the beta parameter, so that would be 0.25, and same for the T lag parameter. To have more detail on this calculation, you can watch the feature of the week number 62, calculating the typical value of each category of a categorical covariate. Note that in this run, we assume that the typical population value is different for formulation A and formulation B, but that the inter-individual variability, represented by the standard deviation of the random effects, is the same for both formulations. So for example, in this case, 17% for Ka. If you want to also estimate different inter-individual variabilities, you can watch the feature of the week number 40, defining a covariate dependent standard deviation of a parameter, or you can use a second method with different absorption models that I will present in a few minutes. If I check what I have in the individual parameter tab, I can see that for each individual, I have the individual parameter values together with the formulation categorical covariate. If I now check what I have in the plots, I can go to the Stratify tab and again use the formulation to color or stratify all the plots. If I check the observations versus predictions, I can also color by formulation and check on log-log scale, and it looks very good. I also would like to have a look at the VPC, so I will generate it in addition. I will first add more bins to see a bit better what is going on, and again split by formulation. And here we see that actually for formulation A, the model predictions, so the blue and pink bands, are below the percentiles calculated from the data, while for formulation B, it is actually the opposite. So something is going wrong here. If I'm checking the results in the test tab, I see that I have a very strong correlation between the random effect for the volume and the formulation. At the beginning, I said that the volume of distribution is expected to be the same for the two formulations. But actually, if I use a KAVK model, the parameter V represents not only the volume, but the volume divided by the bioavailability. So here V differs between the two formulations because the bioavailability differs for the two formulations. One option to take this into account is to add the formulation also on the parameter V, and remember that V represents the volume divided by the bioavailability. A second option is to introduce the bioavailability in the model. I will show you how to do this. I first go to the initial estimates and use last estimates all, and then I will modify the model I have used by opening it in the editor. And in the editor, I will add to the PK model macro an additional argument representing the bioavailability. It is called P, but I actually want to use F as a name for the bioavailability, so I will write P equals F, and add also F here to the input list. I will save this under new name. Close and browse for this model that includes F. I can now add the formulation on F, but remember that F and V cannot be estimated simultaneously. So what I will do is to fix the value of F pop to 1, so that will be the value for formulation A, and then I will estimate the beta that will tell me how much the bioavailability of formulation B differs from the bioavailability of formulation A. Actually, the random effects of F and V are redundant, so I can also remove the random effects for the bioavailability. So I can save this under a new name. Let's call it run number 2. And run again. And this time I will add the VPC to the plots. This time the VPC split by formulation looks very good. The estimated parameters appear here, and you have the beta for f. So I can proceed as before to calculate the typical parameter values. I have decided that the bioavailability for formulation A is 1 considered as a reference, and to calculate the relative bioavailability of the formulation B compared to formulation A, I use the following formula as before and get 0.83. So this was the first option, where the same model with the same equations are used for both formulations, and we just estimate different parameter values for the absorption process. The second option can be used if the two formulations have absorption shapes that differ and therefore require different equations for each formulation. To show you this, I have used a different dataset. This one is for theophylline. The first formulation, called reference, is a TO24. It was the first approved once-daily formulation. And the second one is called euphyllong, and it's encapsulated pellets covered with a porous membrane. So I have loaded this second dataset. If we have a look at it in the data viewer, I can stratify by formulation, and we again see that the two absorptions are pretty different from each other. If I try the first option on this dataset, meaning that I add the formulation as a categorical covariate on T-lag and Ka and fit this model, we can have a look directly at the results, and what we see in the individual fits, where I have highlighted in black the test formulation and in blue the reference formulation, is that the test formulation is pretty well captured by this model, but the reference formulation is not. Although it can have a different Ka and different T-lag value, I see that I actually have two phases during the absorption, a slow one and then a more rapid one. So actually, to capture the reference formulation, I will need a model with a double absorption process. And to do so, I will need a model where I really have a different set of equations for the test and for the reference formulation. In order to be able to distinguish the two formulations in the model, what I have done is to add a ADM column where I have tagged with number 1 the reference doses and with number 2 the test doses. This column, I will tag it as a administration identifier column. Remember that in this column only integers are allowed, so I cannot reuse ref and test, and that's why I'm using 1 and 2. I accept, and I will now load the model I have developed to take into account the two different absorptions. If we have a look at it in the editor, it looks like this. So first, I have set what we have in common for the two formulations. So we have a central compartment with volume V and an elimination with elimination rate K. And then I have first defined the absorption for the test formulation, which in the dataset is tagged with ADM equals 2. So I say that all doses tagged with ADM equals 2 will have an absorption that arrives in compartment 1 with a first order parameter that I have called Ka test and a T-lag that is called T-lag test. I also have added a relative bioavailability relative to the other formulation, so I have called it rel-F. And then I can handle the reference formulation, which has IDM equals 1 in the dataset. I will write two different absorption macros to handle the two different parts of the absorptions that we have seen in the data. So I will first have a fraction f of the dose that arrives in compartment 1 via a zero order process with a duration called tk0 ref that starts only after a T-lag that I call T-lag0F. And then the rest of the dose, so the fraction 1 minus f, also arrives in the central compartment, but with a first order process with parameter Ka-ref, and after a T-lag called T-lag-ref. Actually, I want this first order absorption to start right when the zero order absorption stops, so I have calculated T-lag-ref as the duration of the zero order plus its lag time. So in this model, I have different types of equations for the absorption phase that are described via these macros, and the same central volume and same elimination. All parameters are listed in the input parameter list. I can set up the initial parameter values. For example, I see that my zero order absorption needs to be a bit longer and that my parameter f needs to be a bit more balanced for the two absorptions, and that's good enough as a starting point. So I can set these as initial parameter values. In the graphical user interface, as I have defined in the model, I see appearing here both the parameter for the reference and for the test formulation. The formulation categorical covariate still appears here, but I don't need to use it. It will only be useful to stratify the diagnostic plots. Well, F is a relative bioavailability that can be smaller or larger than 1, so I will keep it with a log normal distribution. However, F is a fraction of the dose that go via the zero order for the reference formulation, so it needs to be between 0 and 1, so I will set it with a logit normal distribution. I can save this under a new name. And run. In the Results tab, I can see the estimated value and have directly access to the typical parameters for the ref and the test formulation. Also note that each formulation has its own inter-individual variability. If I check the individual parameter values, you can see that each individual has a value for all parameters, even if it has received only one of the formulation. Even if part of the parameters are not used for a given individual, Monolix does not know it. So for example, for individual 5, which has received the test formulation, TK0 ref is not meaningful, so the value here is just set to the typical population parameter value. As the value has no impact, you can just ignore this value when you reuse the EBEs for simulations, for instance. If I check the diagnostic plots, I see that now the profiles are all nicely captured. I can also generate the VPC, and it looks very good. So we have seen the two different options, either using the same model or different absorption models in the case of a parallel design. I will now show you what changes if I use a crossover design, where A and B are given in random order during period 1 and period 2, separated by a washout. In terms of dataset, what changes is that I now have a period column that I have tagged as occasions with period 1 and period 2 for each individual. And it is also common, in addition to the formulation categorical covariate, to have the sequence, so either RT for ref and then test, or TR when it's the opposite. I have first used the second method to model this dataset, so including the administration ID column, and in that case everything is the same. So I have used exactly the same model file, and then I have set the random effects on the inter-individual variability level, and if I check this, I can now see in the individual fits the profiles for occasion 1 and occasion 2. So for the second method, in case of a crossover, The only difference is that you need to add your occasion column. All the rest is exactly the same as for the parallel case. Now let's see what happens if I use the first method where formulation is added as a categorical covariate. I still have the occasion column. I have tagged the formulation column as a categorical covariate. If I go to the statistical model tab and I want to add the formulation on TLAG and KA, those boxes are grayed out. This is because the formulation covariate varies between occasions within an individual, so it can be added only when either no random effects are present at all, for example, like this, or when random effects are present at the occasion level, irrespective of random effects being present on the inter-individual level. In my case, I have only one occasion for each formulation, so it will be difficult to estimate both inter-individual variability and inter-occasion variability. So I can decide to keep the inter-occasion variability, remove the inter-individual variability, and add the formulation on TLAG and KA. So this would be how to handle the crossover case. To give you an overview of both methods, so first in terms of dataset formatting, if you want to use the formulation as a categorical covariate, you just need to make sure that you have it in your dataset. If you want to use the second method using the administration ID column, it is convenient to have the formulation column as a categorical covariate just for stratification, and what is really important is to have the administration ID column to distinguish the two types of doses for the two formulations in order to handle them differently in the structural model. The advantage of the first method is that it is possible to use models from our model libraries and then just add via the graphical user interface the formulation as a categorical covariate. If you use the second method, you're going to need to use several absorption macros in the model, and this is for the moment not directly available in the library, so you will have to write it yourself. On the opposite, the drawback of method 1 is that it is not possible to have different inter-individual variabilities for each formulation. The standard deviation of the random effects will be the same for parameter Ka, although Ka pop will be different for formulation 1 and formulation 2. And the second drawback is that you don't get the typical values for both formulations directly in the interface. You need to calculate them from the betas. So both have pros and cons. That's it for today. Have a nice week.